This is notes for compressible flow, stagnation condition, and critical conditions. So let's say we have a convergent and divergent nozzle like this, and this is the ideal condition where we have a gas flow here with certain velocity, and then at throat here, I think you're already familiar with the Venturi meter nozzle, so it's quite the same design. So the smallest cross-section area here is throat, and for ideal design, we hope at throat area here, the Mach number is equal to 1. So because one time ago, it is not easy to get Mach number 1 in throat, because you need to play around with the design to change your compressor here and so on and so forth. So a lot of researcher, it's become an universal terms. So we can call that in throat here, and Mach number will equal to 1, and we call this is a critical condition. So means that if in your question they ask you to find what is the value in critical area and so on and so forth, so you could imagine that that area is at throat and the Mach number is equal to 1. So please remember these terms. And then from throat here, Mach number is equal to 1. And then in ideal condition, we would like to have a faster flow here with Mach number exceed M1 at the exit here. So however, it's depend on the design, it depends on the shock wave and so on and so forth. Sometimes we cannot get Mach number exceed 1 at the exit here. So at the flow here, at any point in the flow, if we immediately stop that flow, we call it as stagnation condition. So if, for example, the flow from point number 1 through point number 2, and at point number 3, we imagine that we could stop that flow immediately. So we could say that at point number 3, the stagnation condition occur. So at stagnation condition, you know the meaning of stagnant here means that the velocity is 0. So we could assume that at stagnation condition here, the Mach number is equal to 0. So this is the three basic equation that you need to understand: T2 over T1, rho 2 over rho 1, and P2 over P1, and P is the pressure. So I hope you could understand this and you could remember to write this one. So and then at stagnation condition, where the Mach number 2 is equal to 0, what you need to do is actually you substitute the value of Mach number here with 0, and then you substitute the value of T1 as T and T2 as T0, T0. So if you solve this equation with Mach number 2, M2 is equal to 0, you could simplify this equation into this one. And it is same for these two equations. If we substitute the value of Mach 2 equal to 0 at this equation, we could simplify this equation into this one. And then if we substitute the value of M2 equal to 0 here, so we could simplify the value of P2 over P1 is this one. So it means that it is not critical for you to remember all of these stagnation condition equation, but the most important is to make sure that you could remember and write correctly, because sometimes students do not remember where to put M1 and M2. So this is the equation for the stagnation condition. And this is the equation for critical condition, as I explained before, at critical condition, we assume that Mach number is equal to 1. And then we use asterisk symbol to show the critical condition terms. So actually, it's come from same equation of this one. For example, to define temperature at critical condition, we have T2 over T1. We substitute the value of M2 equal to 1 here, and then we substitute T1 as T, and T2 is become T star. And then we could derive this equation. Okay, same goes to rho 2 over rho 1. We substitute the value of M2 here with 1, and then we could simplify the value as this one. And then for P2 over P1, again, we substitute the value of M2 equal to 1. We could simplify the term become P star over P and this equation. So this is the equation at critical condition. So normally critical condition is at throat of our convergent and divergent nozzle, and critical condition means the Mach number is equal to 1. So please remember at least this equation. Then please make sure that you understand to substitute the value of M2 to replace the T1 become T, and T2 is equal to T star. And this is the relationship between critical and stagnation condition. I think by looking at this equation, we could substitute from the previous equation. We could have the ratio of T star over T naught, and we substitute the equation, and then we could simplify it into this one. So for example, T star over T naught is 2 over K plus 1. Rho star over rho naught is 2 over K plus 1 by the power of 1 over K minus 1, and P star over P naught is equal to 2 over K plus 1 by the power of K over K minus 1. And then we could determine an expression for the mass flow rate through the nozzle from the equation. For example, this is the mass flow rate. M dot is equal rho AV, and we could replace as P over RT. So this is the equation of rho, and we have A, the cross-section area, and V here we could replace with Mach number third KRT. And then we could simplify everything here into this P over third T, third K over R, A, and Mach number. And then we use the equation for stagnation condition. So we substitute in this equation, so finally we have this term, and then we could simplify it into this term. And then if we choose the critical area where Mach number is equal to 1, we could have the flow rate at throat can be found by using this equation. This shows that the mass flow rate in the nozzle is only dependent on the reservoir condition and the critical area A star. The ratio A and A star can be written in terms of the Mach number as A over A star is equal 1 over Mach number 2 plus K minus 1 M square over K plus 1 by the power of K plus 1 over 2 K minus 1. And here A star is the area at critical area, and A here is any cross section in the flow, and M here is the Mach number at certain point that you choose to calculate. Here I would like to introduce you one table called the isentropic flow for air K equal 1.4. So in this isentropic flow table, so it has a few columns, which is to show you the value of Mach number, the column of P over P naught. So please remember that P naught here is the stagnation pressure, and we have column for T over T naught, the temperature at any point of the flow over temperature at stagnation point. So please remember that stagnation means the velocity is zero. So means that only velocity is equal to zero, but the pressure and the temperature is not necessarily equal to zero. It means that at stagnation point, the velocity is zero, but the pressure and the temperature will give you something, some value. And then this is the A over A star. I think you still remember that previously we learned how to derive the value of area over area at critical. So all of this is being calculated and put in a table like this. So this is the Mach number for certain point, because we have a pressure at stagnation, temperature at stagnation, and Mach number at stagnation is actually equal to 0. So we cannot do Mach number over Mach number 0 because it will ruin the table. So we just list the value of Mach number here. So, and then the isentropic flow table here is specifically for certain gas. So mean for air, so this is the table of the isentropic flow. So if you want to do calculation for hydrogen, for example, or another gases, you must make sure that you have the isentropic flow table with a specific value of that gas. So this is the isentropic flow for air only, which is its K is equal to 1.4. Okay, please take care, please be careful when you use table here. I will show you later on how to use table for our calculation. So it starts from m equal to 0 here, and then we could have it continue here 0 to 0.94 and start 0.96. So we have a 1.9 here, continue 1.9 to 2.9, and finally we could have the largest Mach number is equal to 10 here. So and then because we are dealing with a very high speed, means it might be around 320 meter per second. So you need to calculate precisely. For example, if your Mach number is 1.01, so means that you need to calculate by ratio, because in this table, it is only give you 1 is equal to 0.5283 and 1.02 is 0.5160. So means you need to calculate by ratio here to get what is the value of P over P naught for Mach number 1.01. So I will show you that later in our tutorial lesson. I hope you could download this isentropic flow for air from my website. So you could get this table and then you could use in your calculation